Okay, so today's next lesson is Hamiltonian Circuits and Paths. It actually Hamiltonian Circuits and Paths. Don't worry about the SAS. It stands for Student Assignment Sheet 4. That's from the book. Lesson objective: I can make conjectures and use theorems to determine whether graphs have either Euler or Hamiltonian circuits, or Euler or Hamiltonian paths. Oh, I want to push the button on my phone to make the screen go ahead. Shame on me. All right. How is the voyage around the world problem similar to the Königsberg Bridge problem? We will look at the voyage around the world problem in the next lesson for a bell ringer. So I'm going to pass this up, and we'll look at it in the next lesson after the test. How's it different? Don't worry about that. Okay. How are you, Miss Layton? What can I do for you? Yeah, I know. I got a lot of absence today. I don't know why. So a path on a graph that goes through each vertex exactly once is called a Hamiltonian path. And a path that starts and stops at the same vertex and goes through each vertex is called a Hamiltonian circuit. Now it's a lot different from an Euler circuit and path because they focus on edges there, okay? In this one we focus on vertices, okay? And this is what's the cool part about it is when you focus on the vertices and the nodes, this is a different animal altogether. So let's talk about a practical application for this, okay? Let's say you're planning a trip, okay, around the world, or maybe not around the world, just around the state, and you want to see a few things, okay? Just some, like, highlighted points in Texas, like the Alamo. You want to go to the Alamo in San Antonio. You want to go to the Waco RTC Park, you know, the big ramp swimming park. You know what I'm talking about? You want to go see the windmills out in San Angelo, okay? You want to go up to Fort Worth to go see the stockyard. You want to go down to the Galveston to see the beach, or maybe Matagorda to go fishing. But you want to make it as efficient as possible. You don't want to spend a lot of money on gas. You don't want to spend a lot of money on lodging. So you want to plan out where you're going, take the most efficient route, and go to every spot and not have to backtrack, right? That's where Hamiltonian circuits are really cool, because what's similar about Euler circuits and Hamiltonian circuits? They start and stop at the same vertex, right? What's different? Euler focuses on edges. Hamiltonian focuses on vertices, okay? Notice the word circuit means the same thing in both Eulerian and Hamiltonian circuits, okay? Which of the following graphs does not have a Hamiltonian circuit? Let's look at it. Graph 1, does it have a circuit? Is there a path where you can touch every vertex exactly once? Yeah. Yes. How about graph 2? Can you touch exactly every vertex exactly once? Yeah. The key here is, remember, in Euler you have to touch every edge, which means you can go through vertices as many times as you want. But this one, you only touch the vertex exactly once, which means you don't have to touch every edge. So the same path you took for this one, you can take for graph 2 and touch every circuit, or every vertex, I'm sorry. Can you do it in graph 3? Well, I don't know. It depends on where you start. Okay? Let's say you start here. If you start in the middle, I think there is a possible path, okay? But you can't go back to where you started. You hear me? So, a Hamiltonian path is available, but not a circuit. And this one, it's a circuit. Watch me. Boop, 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 boop. Circuit. Okay, so you really have to pay attention now. There's no whether a circuit or a path exists like in Euler where you can look at the degree of the vertices. In this one, the degree of the vertices and the number of edges doesn't really make it. It does make a difference, and there is a way to do it algorithmically, But it's way more complicated than it needs to be, and it's easier to do these small ones, which is all we're learning is the really theory to it. It's easier just to figure out how to do it trial and error, okay? All right, let's move on. Form a conjecture about when you think a graph might have a Hamiltonian circuit. Now, conjecture is a noun. It's an opinion or a conclusion formed on the basis of incomplete information. I defined this in another class earlier, but I want you to understand we're going to use this word a lot. What is a conjecture? It is an opinion or a conclusion formed on limited information. Okay? Very incomplete information. All right? So what do you think would make a Hamiltonian circuit exist? Is it the number of vertices? No, you can have two vertices and two edges and have a circuit, right? Because you just have two edges going the same direction between the two. You can have three vertices and have a triangle and still have a circuit. The number of edges doesn't matter. Now, if there isn't a... You can say this. Now, think about this. I never thought about this until this year, but as long as you have a pathway between every circuit, you're going to have... or between every vertex, I apologize. Let me rephrase that all together. As long as you have a pathway between every vertex to every other vertex, a circuit will exist. Do you understand why that's true? Yeah, it makes sense now, doesn't it? Because if you've got a pathway to every other vertex from every other vertex, well, a circuit will exist because there's always a path to another vertex. Say you have 6 vertices. You're going to have 5 pathways from each vertex to the other vertex, the other vertices. So conceptually, you can take any path and never cross a vertex more than once and end up at the same one, because you always have a path from one vertex to the other. So that is one you can clearly determine that a circuit exists. If a pathway between every I never said this before, and this is just a conjecture I made up. It's incomplete information, but it's it's not a fallacy. If every vertex has an edge to every other vertex in the graph, a Hamiltonian circuit would exist. Okay? Compare and contrast Eulerian and Hamiltonian circuits. What is the same about them? What is different? We just talked about it in the last slide. You remember? Do you remember the difference and the same, the similarities? What? Compare and contrast. What is the same about Hamiltonian and Eulerian circuits? Anybody? What is the same? Compare them. What is the same? Start and stop the same plot. Yeah, the word circuit is the same, and it's for a very good reason. Because, like Alberto said, they start and stop at the same vertex. Now, let's contrast them. What is different about them? The difference is the focus. What does Eulerian focus on, and what does Hamiltonian focus on? Exactly. Well, Euler focused on the edges and the number, and making sure you only touch them exactly once. Hamilton focused on the vertices and only touching them once. That's very important to understand. As long as you know that difference, as subtle as that is, you should have no problem determining whether Hamiltonian and a circuit and an Euler circuit is that. Now, practical application, what are some situations where a circuit would come in handy? Going into the grocery store and planning out your shopping by item location. That was always important to me. If I worked at Walmart long enough to know where every item in all 2.5 million items are, as a manager, I knew where they all were. So my wife would give me a list, and what normally would take a guy 2 hours to find, it takes me about 20 minutes. Planning a vacation by the sites and events your family wishes to see and partake in. Remember that? Walking across the college campus to get all of your classes in a day. That's an absolutely excellent application for a Hamiltonian circuit. So you get to college, or if you go to college, you won't know that. Texas A&M is a huge university. The school I went to, the first school I went to, Purdue University, was huge. Walking across that campus, when my dorm was on the very southwest side of campus, and I had to get to PT, physical training for the Marine Corps, back in 1984 at the field house. Lambert Field House was on the northeast side of campus. That was almost a mile and a half. Now, that wasn't a big deal because I could always leave early because the first PT's like 6 o'clock in the morning. But then I had a 7:30 class, and I was all sweaty, and I'd be done about 7. I have 30 minutes to get back on campus to the math building for my math class, the math lecture hall, which actually is an engineering building. And it wasn't that far, but I wanted to get home and take a shower, so I had to walk a mile and a half back to my class and then get over to the other thing. It was easier just to go all sweaty and smelly. Most of the time, anybody that was in the Marine Corps was in an engineering class anyway, so it didn't matter. They were all in the same class. Calculus 111, Math 111, whatever they want to call it. Anyway, I needed to know the fastest way to get there, and so I would find my route on the map before I'd take off, and I used that route until I found a better, more efficient route. Anyway, practical application for Hamiltonian circuits exists all over the place. Matter of fact, shooting a rocket into space requires very, very good knowledge about physics, but it also requires knowledge about Hamiltonian circuits and very efficient pathways. All right, can you think of some situations where another circuit would come in handy that you haven't thought of? Anybody? Noah, what would be a good idea of an application that would be practical to you of a Hamilton circuit? Think of destinations as your vertices and the edges as the direction to get there. What are some practical applications you could use this? Traveling, right? Good job. Google Maps has a really way to do that. They use Hamiltonian circuits. And weighted graphs. That weighted graph and Hamiltonian circuits together help Google Maps work really well. I'm going to launch you with this. Most video games require the user to follow a specific pathway through different events, conquer certain opponents, and solve different problems only to return to the starting point. So isn't it amazing that this whole time you'd be playing games like Pac-Man or Zelda that you were following Hamiltonian circuits in proxy, doing problem solving using a mathematical discipline created centuries ago. True story! I think that's pretty cool. Anyway, y'all, that's the end of the lesson. Get on to the assignment. I really appreciate your time.